Welcome back to Kine 3030 Online. Today we're going to look at momentum, mostly angular momentum, although we will talk about what linear momentum is. We're going to define linear and angular. We're going to look at the momentum of a single and a multi-segment body and talk about conservation of angular momentum and transfer of angular momentum. So let's say you are working with a figure skater and you want to work with them on their jumps and you want to get more revolutions in the air. How do you do that? We'll come back to that. Be an example of a problem that uses angular momentum. So momentum in general is a quantity of motion. It's a quantity of motion. In the linear sense, momentum, and I know it's another capital M, same as I sometimes use for moment, which is a torque. There are just so many letters in the alphabet. So in this case, though, it's momentum, and you know that because it's mass times velocity. So the quantity of motion you have can be defined in a linear sense of mass times linear velocity. In an angular sense, the quantity of motion you have, we're looking at very similar parallel measures. So instead of mass, it's going to be moment of inertia. Remember that mass times radius of gyration squared, so it includes both the mass and the distribution of the mass, times the angular velocity. So in angular momentum, you can see that there's going to be three factors that affect. So there were two factors, mass and velocity in the linear, three factors with angular. You've got the mass, you've got that radius of gyration squared, and you have the angular velocity. So that distribution is really important because, of course, it's squared. So increasing mass or velocity will also, angular velocity will also increase your angular momentum. If you have a set amount of angular momentum and you increase the velocity, increase the mass, really can't increase the mass. So if you increase the moment of inertia by increasing the radius of gyration, then the velocity will drop. We'll see that when you have a constant angular momentum. But just understand that those three factors, if they go up, then your angular momentum is going to go up. Recognizing too that your body is multi-segmented and the moment of inertia, the angular momentum, H, for a multi-segmented body is calculated as the sum of the moments of inertia of individual body segments. And therefore, it's, your angular momentum is going to include that sum of the individual body segments. So each segment angular momentum is the sum of two components. The local term, which is the angular momentum around the segment's own center of gravity, and then that segment's angular momentum around the center of gravity of the whole body, so of the total body. You end up then with these two terms, the local term, which is the segment moment of inertia around its own center of gravity, and it's the segment's angular velocity that you're looking at there. So if just that one body segment is rotating in time, that's the angular velocity you're going to look at for the segment. And then you're going to have the remote term, which is the segment mass The r in this case that you're going to square is the distance from the center of gravity of the whole body to the center of gravity of the segment itself. And the angular velocity of that center of gravity, of the segment center of gravity around the whole body center of gravity, which is where your axis of rotation is. So you can see you've got the local and the remote term for each segment. And this shows you that whole piece that you've got the calf and foot rotating around the center of gravity of the whole body. That's the remote term. And you also have the segment rotating around its own center of gravity, which is its local term. And then you would add up that angular momentum for all the different segments to get the whole body. So you would look at the local and remote term for each segment, and then you would add up all the segments to get the total angular momentum, total amount of motion, angular motion for the whole body. A very important factor in angular momentum is conservation of angular momentum. The reality is that once we're in the air, the total angular momentum of the system, when we are in the air, when there's no other torques, external torques acting on the system, stays constant. So if you start as a diver and you take off on your dive and you have a certain amount of angular momentum, that's what you have through the whole thing. Well, what does that mean? Think about what angular momentum, the equation for it is. So angular momentum equals I times angular velocity. Does that mean that if h is fixed, if that angular momentum is fixed, that the angular velocity is fixed? No. H is fixed, but we have this wonderful ability to switch around between the angular velocity and the moment of inertia. So a diver can modify their angular velocity by changing their moment of inertia. How do they change their moment of inertia? Well, obviously they're not going to change their mass in the middle of a dive. Not happening. But if they tuck, you can see them go faster. If they go into a layout position, they're going to go slower because they have a certain amount of angular momentum, and when they increase their moment of inertia by increasing their radius of gyration, which means getting more distributed, which means going into that layout type position, they will slow down, and vice versa. If they tuck, they're reducing the radius of gyration, which is reducing their moment of inertia, which therefore allows them to increase their angular velocity. The diver, as I said, can change their velocity by changing that radius of gyration, and around the principal axis of rotation, which is around the center of gravity of your body. However, doesn't mean because you have this certain amount of angular momentum, it doesn't mean you have to keep it all under the same, around the same axis and around the same direction. You can change your angular momentum that might be in a somersault rotation into a twisting rotation, for example. How do they do that? They do that by doing something that actually, while they're in the air, if you did this, that actually requires angular momentum because you've got two arms going around and it's not symmetrical. that actually is going to take from, because you only have a certain amount of angular momentum. What you took off with is what you have. So if you do something that requires angular momentum, it's going to take it from the other, the angular momentum you have, and it's actually going to change that angular momentum to a different axis. You can do it by doing things around your hip too. So that's when you're air. That's the conservation of angular momentum. I will also say with the conservation of angular momentum, that is the part with the cat, and there's a description in your textbook, and I'm sure you can find videos of it on YouTube, that if a cat ever got fell upside down, they always land on their feet, and they do it they don't have any angular momentum to begin with, but they create angular momentum. So if I'm in the air, or if I'm on something that will twist, like a chair, you can do this if you have a chair that has that rotates. If you go like this, what you'll find is the bottom half of your body rotates, and that's what cats do around several axes, so that when they land, they are on their paws. That's for the angular momentum when you're in the air. It's in the air, you have conservation of angular momentum. There is no external torque acting on you. So how do you get that angular momentum in the first place? And if you want to change the angular momentum that you have to apply an external torque. What exactly is that? We often talk about the idea of an eccentric thrust, which is really just a force. So if I have a force, ground reaction force, that is not going through my center of gravity, that's going outside of my center of gravity, if the actual total ground reaction force, the resultant ground reaction force, goes ahead of my center of gravity, then I'm going to, it's giving me a backwards rotation, backwards torque. That's really a torque. An eccentric thrust is just another term for a torque that isn't going through around your center of gravity. And so if, as I took off, just at takeoff, my force is my ground reaction force before I leave the ground. Once I'm in the air, there's nothing I can do. But before I leave the ground, if that ground reaction force goes in front of me, then I would be doing a backflip. And if as I'm taking off, it went behind my center of gravity, then I would be doing a front flip. So the idea here is that ground reaction force, the resultant ground reaction force, is not going through your center of gravity and as you take off, and therefore you are going to get a quantity of angular momentum before you take off. So that application of torque is not an instantaneous thing. You have a torque over time, and this is impulse. This is angular one, but there's also a linear version, which would be force times time. And it turns out that if you have a large torque over a short period of time, or a small torque over an extended period of time, you could give the same amount of angular momentum. So basically, torque times time, or the area under a torque time curve, is impulse, and that is giving you angular momentum. So whatever angular impulse you give the system will result in angular momentum. And I would highly recommend that you take the time to go through torque times time, or moment of inertia times angular velocity, one being the angular impulse, one being the angular momentum, and you'll see that the units work out to be the same. So a change in angular momentum equals that torque times time, or angular impulse, as I said. So we come back to our diver. Our diver is going to jump in a layout. We have an example of a diver. They jump in a layout position where their radius of gyration is 0.5 meters at an angular velocity of 4 radians per second. And again, it has to be in radians per second, not degrees per second or revolutions per second. In these kinds of problems, has to be in radians. What is the angular velocity when it assumes a tuck position, or a radius of gyration of 0.25? So this is somebody in the air. There's no torques on them while they're in the air, and therefore we're in a case of conservation of angular momentum. So however much angular momentum they have just after they take off in the layout position is going to be the same amount of angular momentum when they go into the tuck position. So we're going to initially figure out what that moment of inertia is, or mass times radius of gyration squared, before while they're in the layout position. So that's going to be 60 times 0.5 squared, or 15 kilogram meters squared. Your angular momentum is then going to be that I times the angular velocity, so that 15 kilogram meters squared times 4 radians per second, or 60 kilogram meters squared per second. And those are the units for angular momentum. They're in the air, so we're going to figure out their new moment of inertia after they tuck. Same mass, 60 kilograms, but now a radius of gyration of 0.25, which will square. So we're ending up with 3.75 kilogram meters squared, which, as we've talked about before, if we, in this case, we halved the radius of gyration, which means we basically divided that moment of inertia by 4. We rearranged and solved for our new angular velocity because the angular momentum is constant. They're in the air. It's not going to change. We have conservation of angular momentum for this diver. So 60 kilogram meters squared per second divided by 3.75 kilogram meters squared, which is the new moment of inertia. And that leaves us with an angular velocity of 16 radians per second. And that shows you why you have to use those radians, because those radians disappear. On the left-hand side, the radians disappeared. On the right-hand side, the radians reappear because it's a unitless unit. So we know that it represents a change in angle over time, because that's what angular velocity is. So we just put in that radians back in. So we're going to watch now a video. We're going to come back to our original problem, which had to do with how do you get more revolutions out of a figure skater. I'm going to show you this YouTube video.
Every 4 years, we watch the stakes for Olympic figure skaters get higher as they try to increase rotation in the air with their triple axels and quadruple toe loops. How do they do that? It's a scientific principle that we asked Olympic hopeful Rachel Flatt and Deborah King, a sports scientist funded by the National Science Foundation, to help explain. Figure skaters make it look so easy, leaping off the ice, rotating through the air, and landing in a graceful arc. But make no mistake about it, figure skating is one of the most demanding of all the events at the Winter Olympics. For 17-year-old Rachel Flatt, the demands of training for the Olympics have to compete with other demands.
I basically head to the rink at around 6 o'clock. I skate from 6:30 to 7:15. And then I go to school from 7:30 until about 12:30. And then from there, I go straight back to the rink.
When she's on the ice, this AP physics student might want to consider the science that goes into her every jump. To see this science in detail, Rachel agreed to train in front of a special high-speed camera called the Phantom Cam. It has the astonishing ability to capture her jumps at rates of up to 1,500 frames per second.
It's very cool watching myself on the Phantom camera. You get to see every phase of the jump, and it's pretty incredible just to be able to see every aspect of it, where exactly the placement of your arm is and where my head is. Everything is very cool.
We brought the footage to Deb King, a professor of sports science at Ithaca College and an advisor to United States figure skating.
A figure skating jump is a really complicated skill that combines a lot of different motions in it. They need to really optimize a lot of different conditions in terms of speed, force, vertical velocity, generating angular momentum, and put it all together in a package with just the right timing to execute the skill.
Deb watched the Phantom Cam footage to explain what Rachel needs to get height and speed in one of her jumps. The first factor is angular momentum.
In figure skating, angular momentum determines how fast you're going to be able to rotate in a jump in the air. So when you do a spin, if you generate more angular momentum, you have the potential to spin faster.
Going into her jump, Rachel generates angular momentum by pushing off the ice with her foot. Pushing off the ice also generates vertical velocity, which will help Rachel get high enough to do her spins.
The vertical velocity comes from producing forces from the jump during takeoff. This is sort of where action-reaction comes into play. As they contract their muscles and really powerfully extend their leg, they're pushing down against the ice. The ice will create a force up on them, which gives them vertical velocity. And it's pretty much the laws of projectile motion that the more velocity you have at takeoff, and this is vertical velocity, the more she can keep going fast, straight up, the higher she'll jump.
When Rachel spins on the ice, she exploits a law of physics to rotate faster and faster, almost as if by magic. How does she increase her speed while she's spinning? The answer lies in her arms. When Rachel first starts to spin with her arms extended, she rotates slowly. But as she pulls her arms in closer and closer, she starts to rotate faster and faster. Rachel is following an important law of physics, the law of conservation of angular momentum. You can't go to jail for breaking this law. In fact, you can't break it at all.
As you get a smaller body position, your speed goes up. If you get a bigger body position, your speed goes down. So they react in the opposite directions.
Back in her office, Deb King spins on an office chair to make the same point.
What I'm going to do is when I'm spinning, I'm going to go from a really open position to a tight position, and you'll see my speed change. So let's give that a try. So this is pretty fast, slower, fast, slow, fast, and I'm going to keep going, and the only way to stop is going to be put my foot down and grab the table. I'm really dizzy right now.
If Rachel can keep her body straight and hold her limbs in close, she'll achieve a higher rate of speed. But it's not as easy as it looks.
It's hard to stay as straight as possible with every force. You're basically being pulled out everywhere. So it's easier to stay in when you're crossed with your hands and your legs. It just makes the jump more efficient.
But no matter how much attention she pays to the science of her jump, Rachel's road to the Olympics will depend on her making skating look effortless.
You never know what's going to happen. The unexpected is, it's amazing.
So, coming back to that problem after you've seen that video now, you have several elements that all go together. The reality is, when this person is in the air, they're a projectile. So you need to have the highest vertical component of the velocity as you possibly can, because the higher the vertical component of the velocity is at takeoff, the longer they're going to stay in the air and the higher they're going to go. The longer they're in the air, the more opportunities they're going to have for revolution. So that first part, they go as fast as they can, and then they dig in order to convert that horizontal velocity that they have while they're skating along the ice up to a vertical velocity up in the air, is to make them into a projectile, and to take that horizontal momentum that they have, mass times velocity, into a vertical momentum and a vertical takeoff component of their velocity. So that gets them up in the air as high as they can go, as long as they can stay up there. To get the twists, they have to have that eccentric thrust around the spin axis. So as they're taking off, they have to actively spin as they're taking off, so they can still transmit that torque to their body, and which is the angular impulse. So a torque times time. So that by doing that, the skates will actually transmit a torque to the skater, and so that they have a certain quantity of angular momentum as high as possible when they take off. Once they take off, once they're in the air, and they're spinning around that axis, they're going to want to come in as close as possible and as tight as possible. You often see them cross their legs too, so that their legs don't spread out. And in here, so that is the smallest radius of gyration possible that you can get around your the spin axis, and that will increase their angular velocity. Once that angular velocity, or once they're about to come back down, they spread out, because if they landed while going that velocity, they would fall. So they actually do have to, not really talk about it there, but you have to do the opposite thing just before landing. You have to spread out so that when you land, you're not spinning as fast as you could be. So those are, that's angular momentum, and recognizing that something like a spin problem like this is actually a combination of projectile motion way back from the first part of the course, and angular momentum together, which is going to give you that, in combination, the most revolutions possible. So we've talked about linear and angular momentum, and how angular momentum is created around a multi-segment body, and that conservation of angular momentum and how important that is, particularly in things in the air. We'll see you next class.